Morning, everyone. Yeah, hopefully, me and Richard will keep us on schedule. And and I'm Sam with Peter's Research fairly recently, and you'll hear from Richard later. Though I'm sure you've all heard many things from Richard over the years, and so at the moment, simulation we make simulation software, so it helps you choose number, size, speed of your lifts in high-rise buildings, and we're also now using it for writing dispatching algorithms. At the moment, we have simulation is individual people. Got this person comes along at this time and they want to go here, which actually in the real world isn't particularly realistic. In the real world, people come along, groups, all sizes, especially airports. You often have families traveling together. Offices, colleagues may have met for coffee before work, and they end up coming into the office together. So if you want 6 people for 5 minutes, 6 people show up, and at the moment, a random number generator puts them somewhere in this 5-minute period. However, it doesn't account for 2 people showing up at the same time. And also, when we start accounting for batches, instead of having 2 periods of 5 minutes, we can have 1 period of 10 minutes, which allows for a more realistic spacing of people. So rather than having 6 people, you can go for 5, 7, 4, and if you went further, it gets more varied and more realistic. And I'll now pass over to Richard to explain how we are generating the batches we're using for our simulation.
Thank you, Sam. So, as many of my work, I often end up finishing off what other people have started. Done a lot of work, continue a lot from what Gene has done, and also Lufti, every time he gives a presentation, I think I need to do some more work on that. This paper was one Lufti and I did together on creating batches in simulation. And we first of all, we looked at different ways you can generate passengers in simulation. So lots of simulations do generate passengers in different ways. And in the paper we presented a couple of years ago, we looked at the different possibilities of doing that. And we came up with a method which allowed for batches and also was more consistent in its use of Poisson in the arrival rate process. There's an elastic band there, that's not a mistake, and I'll talk about how that works in a moment. Limitations of what we did in that last paper. One was that when we generated passengers, we had, at the beginning of every period, we had a passenger arrive. When we are creating in simulation traffic flows, which might vary, we might have many different periods, and we're linking them together. And so what happens, sorry, it's adjusted right. So what happens if we have a passenger arriving at the beginning of each period is that it's unnatural, because we don't always, every 5 minutes, have one person arriving. So that's one of the issues with that. And the other issue was we had to use a table of batch sizes. So we had to tell the software that I've got a certain proportion of number of people who are going to be using, coming in batches of 1, a certain number of people are going to come in batches of 2 and 3, and so on. So we wanted to simplify that for users. We also needed to collect some more data, and we still need to collect some more data, but the only table that we've had up to now is actually this one, which was collected by Coney, Marilisa Sokonon and her colleagues. So we want to collect some more data. So first thing we did was we went to a building and we measured 1,249 batches. So this is people are coming together. So the individual people are traveling on their own. People in twos. You can generally, when you observe, you can see when people are together. And this is a major transport terminal, so there were actually occasional very large batches. So that's a distribution. And what we thought is, could we use Poisson approximation, the Poisson formula, to best fit batches based on the average batch size? And what the next graph shows you is the green is the measured batches, the actual number of batches we saw, groups of 1, groups of 2, groups of 3, and the equation is the black triangle. So you can see from that that we can model very, very closely. Just from one average batch size, we can generate all these different possibilities. And the other thing we've done is in the generation process, we've created a ghost person at the beginning and end of each period, and that allows for, this avoids having the person on the start of the period. So, an example, let's assume we've got 7 persons per 5 minutes. So our user has asked for 7 persons per 5 minutes, and in this instance they've got for simplicity, I've got a very large average batch size, so it's 1.7. So the average grouping of people is 1.7. Yeah, so we've got 7 persons per 5 minutes, a batch size of 1.7. So what first thing we do is we generate 7 people, because we want to give the user the number of people that they've asked for. And if you use just straight Poisson, sometimes you get 6 and sometimes you'll get 8. Actually, we want to give them 7 because they've asked for 7. We then break them up into batches. We can do this equation. I won't go through the equation now, but it's a function of the batch size, and the n is the number of people in each batch. So these 7 people I've now broken up into 4 different batches. There's 2 batches of 1 people, and 1 batch of 2 people, and 1 batch of 3 people. And then we use this equation to put them on the timeline. So you can see I've got a ghost person here, and I'm going to throw my dice and create this delta t and put the first person here. I'm going to throw my dice again, put the second person here, and throw my dice again, put those people, that batch of people there, and so on. And then we actually have to create a ghost person at the end as well to place this one, so we know where actually the end of the time period is. Okay, so let's say we've done that and we've got some numbers. What happens here, because we've got this random element, although we wanted 7 persons per 5 minutes, we ended up with a time period of 310 seconds, which is just over 5 minutes. And then what we do is, which was what was Luftig's idea, was we then stretch time. In this instance, we're actually squashing it. So we bring the 310 down to 300, and we get the people are just slightly close together. And the final element of the equation of the process is the destination where people are going, and this corresponds to a destination probability of 10% for each floor. Again, we throw another dice, and if the random number we have between 0 to 1 is 0.15, so that's greater than 10% but less than 20%, then that person would go to 2. And if it's greater than the sum of those 2, it would go to 3. So that's how we do destinations. So I've worked very hard to catch up on time. So the conclusions, passengers arrive in groups. So we can do simulations with passengers arriving in groups. I've showed you, and I've given you an overview in this presentation of how that is generated. There may be better ways of doing it, but that's actually why I'm presenting it, and that's why we've written that down in a lot of detail in our written paper. Because when we compare simulations, there are many things in simulations which are different, and we all say we're going to generate 7 persons per 5 minutes, say, but actually I might do it one way, and Coney might do it another way, Schindler might do it another way, Adrian might do it another way. There are many different ways of generating, so we want to be clear on how we're doing it, and if there's a better way of doing it, we'd love to hear that presented. So we've had 2 papers so far on creating batches, actually a lot of work done previously by Coney about creating batches. We think this is a nice way of generating passengers, and we described it in total, so it's for people to come back and say, there's a better way of doing it if you've got it. We need more survey data. The reason we need more survey data is we want to be able to provide guidance in guidance documents like Guide D, what the average batch size is for different types of buildings, because it does actually make difference in your simulation results. It can be quite significant. So it might be that in an office building, the average batch size is actually only 1.05 or something like that, and it's not particularly significant. At lunchtime, it might be a bit more. It might be 1.008 or something. In an airport situation, it might be 2.4 because people are more likely to come in groups. I don't know what it's going to be in a hotel. But that's information that we want to collect and to be able to provide some survey data. It's just one part of simulation, but it's an important part of it. Thank you.